In this session, we are going to talk about 11th Physics, chapter number 4, Laws of Motion, part 3. First point is conservative and non-conservative forces and concept of potential energy. Consider an object lying on the ground is lifted and kept on a table. Neglecting a resistance, the amount of work done is the work done against gravitational force and it is independent of the actual path chosen. Similarly, while keeping the same object back on the ground from the table, the work is done by the gravitational force. In either case, the amount of work done is the same and is independent of the actual path chosen. The work done by force vector F in moving the object through a distance dx can be mathematically represented as dw is equal to du or du is equal to minus vector F dx. If work done by or against a force is independent of the actual path, the force is said to be a conservative force. During the work done by a conservative force, the mechanical energy, that is, sum of kinetic and potential energy, is conserved. In fact, we define the concept of potential at a point or potential energy with the help of conservative forces only. The work done by or against conservative forces reflects an equal amount of change in the potential energy. The corresponding work done is used in changing the position or in achieving the new position in the gravitational field. Hence, potential energy is often referred to as the energy possessed on account of position. In the above illustration, the work done is reflected as increase in the gravitational potential energy when the displacement is against the gravitational force. Same amount of potential energy is decreased when the displacement is in the direction of force. In either case, it is independent of the actual path but depends only upon the initial and final positions. This change in the potential energy takes place in such a way that the mechanical energy is conserved. As discussed above, increase in the potential energy d is equal to minus vector f dx, where vector f is a conservative force. During this process, if the friction or air resistance is present, additional work is necessary against the frictional force for the same displacement. This force is strictly path dependent and not recoverable. Such forces like friction, air drag, etc. are called non-conservative forces. Work done against these forces appears as a heat, sound, light, etc. The work done against non-conservative forces is not recoverable if the path is exactly reversed. Next point is work done by a variable force. The popular formula for calculating work done is W is equal to Fs is equal to Fs cos theta, where theta is the angle between the applied force F and the displacement S. This formula is applicable only if both force F and displacement S are constant and finite. In several real-life situations, the force is not constant. For example, while lifting an object through several thousand kilometers, the gravitational force is not constant. The viscous forces like fluid resistance depends upon the speed, hence quite often are not constant with time. In order to calculate the work done by such variable forces, we use integration. Figure 4.1a shows work done by non-linearly varying force, while Figure 4.1b shows work done by linearly varying force. Illustration from Figure 4.1a, which shows variation of a force F plotted against corresponding displacements in its directions. As the displacement is in the direction of the applied force, vector nature is not used. We need to calculate the work done by this force during displacement from S1 to S. As the force is variable, using work F of 8 minus 5 directly is not possible. In order to use integration, let us divide the displacement into a large number of infinitesimal, that is infinitely small displacements. One of such displacements is ds. It is so small that the force F is practically constant for this displacement. Practically constant means the change in the force is so small that the change cannot be recorded. The shaded strip shows one such of displacements. As the force is constant, the area of this strip, FDS, is the work done dW for this displacement. Total work done W for displacement S2 minus S1 can then be obtained by using integration. Therefore, W is equal to integration from S1 to S2 FDS. Method of integration is applicable if the exact way of variation in F with S is known and that function is integrable. The area under the curve between S1 and S2 also gives the work done W if the force axis necessarily starts with 0, as it consists of all the strips from ds between S1 and S2. In figure 4.1b, the variation in the force is linear. In this case, the area of the trapezium A S1 S2b gives the total work done W. Thank you.